Hi, this video is an introduction to thinking about electric charge and electrically charged objects. So a symbol for electric charge, it's not the only symbol that people use, but it's the one that, for example, I went to school and saw, is either a capital Q or a lowercase q. Yeah, I'm not sure why historically that was the symbol that got used. But anyhow, the basic reason that the things around us can become electrically charged is because the things around us are made out of atoms, and atoms are made out of protons and electrons. Electrons are negative and protons are positive. So the charge of an electron, that's what I'm trying to say right here, has the value negative E, where E is a fundamental unit of charge. And it's a standard thing. So the charge of the electron is negative E, and the charge of the proton is positive E, right? So this unit called E is the amount of charge that electrons and protons have. And every electron has exactly the same amount of charge. It's negative E. And every proton has exactly the same amount of charge, positive E. And so you can see that the amount of charge that one proton has is the same amount of electric charge that one electron has, but it's just that they have a relative opposite sign between them. So E is not the SI unit. It's a fundamental unit of charge, but it's not the international system unit. That unit is called the Coulomb, and it's named after a scientist from some time ago that studied carefully quantitative aspects of electricity. And that symbol given to the SI unit called the Coulomb is just capital C, right? Capital C because it's the name of somebody. And 1 Coulomb of electric charge is about 6 times 10 to the 18th electron charges. So that's a pretty big number, right? You might wonder, like, so if I have an electrically charged piece of metal and I'm holding onto it and it's in the room, maybe we're talking like 1,000,000 electrons, right? Which is a really, really small fraction of this Coulomb. Yeah, so maybe 1,000,000 electrons worth of charge on an object that you might have caused to become electrically charged, right? Let me clear this drawing up just a little bit. There's too many things that look like equal signs. So here are some basic rules, and you're going to learn a much more formal way to think about the rules. It's actually called Coulomb's law later, but for now, here are some basic things. Oppositely charged objects attract. So since atoms are made out of electrons and protons, you can see why these things might stick together inside of an atom. And it's because electrons and protons are simply oppositely charged, and they tend to attract each other. So they want to stay around. There are forces that cause them to accelerate towards each other, right? That's what attraction means. But the sort of opposite scenario is when two charges are the same sign, either minus and minus or plus and plus. So like charges repel. So a couple of electrons, they don't want to actually stand that close to each other, so they repel each other. Two protons are also going to repel each other. And another detail, so opposites attract, likes repel. That's how you understand whether or not you're going to have attractive forces or repulsive forces. But also the forces in either repulsion or attraction, in both cases, whenever the electric charges are closer to each other, like down here, whatever the interaction is, it's just going to be stronger. So this is going to be a strong repulsion. Whereas this situation where we have an electron and a proton kind of far apart, this is something of a weak attraction. Okay, so those are basic rules about how to sort of start to model how electric charges interact with each other. Right, and that's very physicsy. Physicists like to model things, like how to guesstimate what's going to happen based on some facts about the little piece of nature that you're watching. Okay, so here is another basic fact. So we don't tend to study individual electrons and protons, although you can imagine doing so, right? We tend to study materials. And materials fall into generically two different types of materials. One's called a conducting type, and metals, any metal, any metallic object is going to be a good conductor. And then the other, sort of the opposite type of a material, is called an insulator. And so examples of insulators include glass, rubber, plastic. And in fact, actually, a really good insulator that's often not mentioned as an insulating material, because people always forget it exists, is just the air. On the surface of the Earth, you know, we have our atmosphere, which is air, and this air is an insulator, electrical insulator. Basically, conductors, they, in a sense, allow the electrons within the metal to freely move around, right? Still, the issue is the electrons are going to repel each other, so there's a certain limit to how far they can move around on the material. They tend to spread out sort of homogeneously through space or throughout the material. But if there is a reason for the electrons to move around on a metal, then the metal sort of allows it. And the idea is metals, right, are composed of atoms that are metallically bonded to each other. And in those metallic bonds, there are so-called free conduction electrons. Some of the electrons in the metallic bond are stuck in the bond and they can't move around. So those electrons can't get very far from their atoms. But other electrons in that very same bond, they actually don't necessarily belong to the atoms that they are nearby. They sort of belong to the entire metallic object. That's really different from an insulator type material like glass or rubber or air. Those materials, they do not have these so-called free conduction electrons. That doesn't mean the electrons can't move. They can move a little bit, but they can't move as wide-ranging as what happens in metallic objects. Okay, so let's talk about how you might cause this electrical phenomenon to show up. How does an object become electrically charged? And the basic issue is an object becomes electrically charged if there is an imbalance in the numbers of electrons and protons. That is, if the number of electrons and the number of protons in our object, if these two amounts are not equal, then we're going to have an overall electric charge, and that's referred to as a net charge. And the net charge really is, it's as simple as taking the number of protons in our object and subtracting the number of electrons in our object. And this difference describes the imbalance, right? That's called the net charge. So here is a basic physical fact that's useful for when you are modeling how electric charge might be moving around, getting removed or added. And this is pretty important. The only charge that you're going to tend to be able to add that is add extra, or subtract, that is remove from the object, is electrons. You cannot move the protons. The protons, in some very real sense, the protons are the object itself, and what we are trying to do is not change the object itself, not change the mass of the object or the size of the object. We're actually trying to just change the charge of the object. And the way we do that is you imagine only changing the numbers of electrons. That is, you can add extra electrons or you can subtract electrons from the object, but you're not adding and subtracting the protons. When you do that, you are making your object more massive and bigger or less massive and smaller. That's what happens when you add and subtract protons. So, when you are thinking about charging up your object, when you're thinking about adding and subtracting electric charge, it's useful also to realize while you're modeling that different types of materials, like even different types of plastics or different types of natural materials, like the difference between fur and wool, even those different materials hold on to their electrons with different strengths. So this is the beginning of having a whole bunch of fun with home experiments. And if you're curious about doing some experiments at home, you might look up the word Triboelectric series. And you can see which objects tend to take electrons and which objects are more happy to drop electrons. This is referred to as the Triboelectric series. And it shows you the difference between, say, rubber and glass and plastic and copper, for example. Okay, so on the sort of tip of thinking about modeling, I'd like to describe to you a particular way you might use this triboelectric series, if you wanted to cause objects to become charged. So there is a basic way to do this. It's called charging by friction. And what you need is some warmth, like a warm environment. And actually, you know what else helps is if the environment is dry. So an example where this sort of situation shows up, where you have a warm environment that's fairly dry and the various different objects are very close to each other, and maybe even some friction forces involved, right? This is what you get in a dryer, right? And in particular, you might have had the experience of trying to remove a wool sock from a polyester shirt, right? That's been in the dryer for a long time. So the particular example that I have is using wool, which is one type of material, and rubber, which is a different type of material. And it turns out that if you were to check the triboelectric series, it would show you that what's going to happen between rubber and wool when they are rubbed against each other, right? So here is some wool, and the other thing is, say, a rubber balloon. When you rub these two things on each other, electrons from the wool move over to the rubber balloon, right? So this is it's as if, like, if you played it out, right? You would have a little proton next to an electron and another electron and another electron, and there are some protons. And when you do this process of rubbing these two things against each other, this little electron right here is going to move over to the rubber balloon, and this one is too, and this one is too. But I'd like you to be very, very careful to note that absolutely not every electron from the wool moves over to the rubber balloon. Some really, really, really small fraction moves over to the balloon. most of the electrons in the wool stay in the wool, but some super tiny fraction of them might move over to the rubber balloon. More electrons will move over if you cause this process to happen even more vigorously, but there will be some limit. You can't get that many electrons over, but the idea is you can. So let me draw that, right? So the electrons have moved over, but remember what I said, the protons don't move. We're talking about only the electrons moving over. And so the net charge, you can see that the net charge of the balloon here is 0, and the net charge of the wool is greater than 0, right? So the net charge of the balloon is negative, and the net charge of the wool is positive. Overall, actually, no electrons were broken or destroyed. Charge wasn't gotten rid of, right? Actually, there's an overall conservation of charge, turns out. So, for example, if the balloon became charged to, say, negative 0.5 coulombs, then absolutely, if the charge didn't get to go anywhere else, then the charge of the wool would be positive 0.5 coulombs, right? Can you see that? It's just an exchange of charge. That's what's meant by conservation. It can move around, change ownerships, but charge cannot be destroyed. Okay, so I've described charging by friction. Let me complete the picture by using the charging by friction to now charge by induction. So you can see I've got this rubber balloon. It's here. So here's the rubber balloon, R for rubber. And this thing right here, next to it, is a metal sphere. And you can see that on the metal sphere, I've shown it. So the electrons on the rubber balloon right here, they repel the electrons on the metal sphere away from the left-hand side of this metal sphere. But the electrons, because they are surrounded by air, which is an insulator, the electrons can't conduct over into the air. The air blocks them. It says, no, you can't come here. We don't have a place for you. You can't conduct around in the air. So they stay on the metal. But they came from the left side, and the protons can't move around, right? Because the protons aren't allowed to move, just the electrons. So the electrons essentially just shift over to the right. And what happened to the metal sphere in this case is the metal sphere is polarized. That's what's being shown here, where one side is positive, the other side is negative. But can you see that the net charge actually is still 0? But the charge is distributed, interestingly, and that's called polarization. And this polarization was actually induced. But now I'm going to show you how you might electrically charge this metal sphere with this induced polarization. So you can see there's another metal sphere over here, but it's really far away. So nothing is happening to it, because remember that when things are further away, the forces are weaker, so the effects are weaker. So this is far away and nothing is happening to it. So what I'm going to do is I'm going to take this thing and I'm going to bring it closer to what's going on over here with this induced polarization. So I'm going to keep the rubber balloon here. So here is this rubber balloon with its negative charge. This metal sphere has this positive charge on the left and the negative charge on the right. And the other metal sphere, if I bring it close and actually touch, what's going to happen is, actually, let me not touch it quite yet. So it's still got this air gap between, so this insulating air gap that the charge can't travel through. So what happens is the negative charge on this sphere moves over to the right because the electrons are actually repelled from the negative charge that's sitting on the right side of this. And actually also, even though it's further away, it's not a zero effect. It's just slightly weaker. But can you see that the negative charge on both the rubber balloon and the metal sphere push the negative charge on this metal sphere over to the right, which leaves over positive charge on the left side of that sphere, right? Okay, so let me erase these marks. And then what I'm going to do is I'm going to bring this metal sphere closer until there is no more air gap. That is, I'm going to cause the two metal spheres to touch, and the electrons can flow across that small touch point where there's no insulator between because the metal spheres are touching. So let me do that. So now the metal spheres are touching. And let me draw the charge real quick before the electrons move across. But can you see what's going to happen? These electrons that are right here have a way to go and sit on the right side sphere. They can just move across the touch point between them. So let's move those electrons over. So here they are instead. And when they do that, what's interesting is when the three electrons leave the metal sphere on the left, they leave behind residual positive charge. So let me erase the changes. And in a sense, these extra negatives cover up these old positives. And so now, when we separate the two metal spheres, we have a metal sphere here and a metal sphere far away, and the negative charge can re-spread out over this metal sphere. And this metal sphere sort of redistributes how its charges exist on it, right? But plus, see, you notice I put 6 pluses and 6 minuses. So, and you can see that the charge is conserved, like the total charge didn't change, but it just moved around. And now this metal sphere and this metal sphere, if I take the rubber ball far away, so its effect, its influence isn't close enough to be strong, then I've got two metal spheres, and I have induced net charge, right? And this is called charging by induction. It's induction because I induced a charge separation because of the proximity of a charged object, right? So inducing is kind of like a non-touch way of causing charge to move around. Okay.